All right, let's get this slide set up. Now, a couple things to say first. I think we already did that slide, so I think we're going to start at the next slide. But before I move on there, let me think. Main thing, I guess, is that the vice president did want us to read in class about people who haven't paid, needed to pay by the day or they will be removed from class. Well, of course, this is my perfect class, right? All of you are paid. Very good. So I don't have to do that, except maybe you have friends that are here and maybe they haven't paid. Please let them know if they don't get something done today, they'll be removed from the class. Now, that something means, number one, paying. But number two, even if they can't get it paid today, they need to contact someone in the business office on this campus, it's the cashier's window, and let them know what their situation is and what their plans are and how they're moving on it. And they can do a waiver or a flag on the account to keep you from getting removed from the course. So if you know of anyone in the course, in school here, that may not have paid, please let them know they need to do something today. Preferably to pay, but if not, yeah. The other thing, and this I don't think will bother either one of you either, but I normally have office hours on Fridays on the Birmingham campus, 7:45 to 11:45. Not this Friday. The dean or someone's called a meeting for 12:30, so therefore I have office hours from 7:45 till 12:30, and then I'll be at the meeting, and then I'll be going home. So actually my office hours are a little longer. I'll probably leave a little before 12:30 to be there at 12:30, but I'll be there a little bit longer today. Okay, or Friday. All right, any questions before we get started on today? Okay, what we're doing now is flow rate. And let me give you, and these are fairly standard kind of abbreviations, not always, but fairly standard. The flow rate, let me get my pen set up. All right. Flow rate, for some reason the pen's not working well, is usually Q. Now, to me, more important than what the symbol is, what do we mean by flow rate? How much flow per unit time? Okay? Now that could be, if it's a liquid, we might have it in liters per minute, gallons per minute, okay? But quite often, especially if it's a fluid, not necessarily a liquid, then we measure usually in cubic feet per minute, cubic meters per minute, cubic centimeters per second, something like that. So it's some quantity, and it could be a capacity, like quarts or gallons or something like that, or liters, or it could be a volume, like cubic meters and cubic centimeters, cubic feet, whatever. It's a volume per unit time. That's what this stands for. Volume per unit time. Okay. Now, how do we classify the volume? Either in a capacity measure, but more likely a cubic linear measurement, cubic feet, cubic meters, something like that. Okay, now, here we have a pipe through which flow is going, okay? Now, I've already written on this, I guess I can still blow it up. I'll just lose what I've written, but that's okay for now. All right. Here's a column of fluid flowing past some point P in 1 unit of time. Well, what that is, in a unit of time, depending on the velocity of the flow, and the unit of time, let's call it a second or a minute or an hour or a century or whatever the unit of time is, the velocity times that time, okay, hold off on that for a minute. The velocity is in centimeters per second, for instance. Now, this is really poor. Yeah. What a terrible way to say that. Number one, if it's velocity, that would be centimeters per second, not centimeters. Okay? Now, I can't believe they mean that to be a length. I think they mean that to be a velocity. Which makes no sense. VT would be a length, and that would be in centimeters. So either this should be VT in centimeters, or it should be V in centimeters per second. It's just a really lousy. But they're saying velocity as physicists would go crazy with this. That's why I'm having a problem with it. I guess mathematicians don't care. Okay, but anyway, the velocity, it would be centimeters per second times a second. Then this would be how many centimeters it goes in that second. Okay, that's what they mean. It's the velocity rate times 1 second. That's why they say that, and that would give you. So yeah, I see what they're saying now. The amount of velocity, say 30 centimeters per second. So in 1 second, that would be 30 centimeters. Multiply V with, if V is 30, that's what they're saying there. Yeah, that's a terrible way to say it. Okay. VT would be in centimeters, and if T is 1 second, then that works better. Okay, so that would be how far it travels. Okay? Now, the area of that cross-sectional piece of the pipe, if that's a circle, it could be something else, but let's call it a circle, then the area there would be pi r squared, where r is the radius of the pipe. Okay? And then pi r squared times v, okay, would be the column of fluid going past P in 1 unit of time. So this would be an area times a length per second. So that would be cubic centimeters per second. That would be your flow rate. Okay? I really don't like the way they express that. But see, this hat carries with it per second. That's why this should be centimeters per second multiplied by area would give you cubic centimeters per second. That's your flow rate. The column of fluid past P in 1 unit of time is that. So in 1 unit of time, that's per second. So it says the same thing, just a really strange way of going about it. Okay. All right. Now, let's back up one more. Okay. Now, so they say, is this flow rate Q equal to the cross-sectional area, pi r squared, say, times velocity? Okay, that's what that thing says. Okay, well, the units work fine, okay, because this would be square centimeters times centimeters per second. That would give you cubic centimeters per second, and that would be a great volume per time flow rate. So that would be fine. Is that reality, though? Generally not. Can you think of why? That would be reality if this was frictionless flow. In other words, the fluid moving through there was perfectly slick, the pipe was perfectly slick, and there's no friction there at the edges. Then that would be all we had to do. But in reality, pipes are not perfectly slick. Fluids don't go sliding past them perfectly. In fact, there's always friction. Now, you think with a fluid there's not much friction, but there always is friction. Always. Something retarding the flow. Okay? So this doesn't quite work. Okay? In reality, the fluid particles do not all travel at the same velocity because of friction. Therefore, for a slowly moving fluid, the flow is laminar, by which we mean that the velocity depends only on the distance from the origin. So let me give you the better picture. That would be if you had frictionless flow. Yeah.
Is that centimeters cubed seconds? Minutes?
Oh, minutes. Okay, I'm sorry. Whatever your time unit is, okay. If you're measuring cubic centimeters per minute, that's going to be a pretty large measure, I would think, unless you have very slow flow. Cubic centimeters are that would be your little fingernail across little fingernail, yeah, that's a cubic meter. It would be pretty small. And if you have to measure how many of those pass through in a minute, you got pretty slow flow. Okay, pretty slow flow. I would say those would be more typically measured per second. It's just a time measure, whatever your unit of time. You're right, the book says minute. Okay, it says per unit time, then they threw in the minute. Okay. Things that, if you measure your fastball in centimeters per minute, it's not a very fast fastball. Okay, yeah, never mind, you wouldn't do that. Okay, all right. If you did, don't let a base runner get on there, because by the time it got to the plate, he's already stolen 3 bases. Yes, never mind. We won't go there. Okay. All right. This is a little closer to reality, and I find this a really backwards-looking illustration. It bugs me every time I see it, but it's typically what they show. I mean, it's not just this book. It's sort of what they show. If I were doing this, I would take the cross-sectional area here and put the arrows at a common thing, and then have the flow being the shape. They say start from a parabolic shape and let that go, and then they'll all reach there at the same time, which to me is not how things are normally done. But it's okay. But this is more close. This is not laminar flow. You always have frictions on the edges, so you always have the slowest velocities there. Your greatest velocity is in the center. And I mean, if you were to reach up there and feel, near the edges you feel almost no flow coming out because it's fluids, it's gases or liquids. But in the center of that, you don't have the greatest flow because there's always frictions at the edge, friction at the edges. So this describes laminar flow. Now this is still pretty slow flow because you don't want any eddies in there. You want it just to be forward-moving flow. None of the velocities get going. And you know, if you really turn up the volume too much, you get a lot of eddy currents in there. That would be turbulent flow. This is laminar flow. Turbulent flow is very hard to measure or model. Laminar flow is a lot easier. So keep the flow slow enough so you don't have any turbulent flow. This is laminar flow. Increases toward the center of the tube, decreases toward the edges. Now you only see the dimensions here, but you know this is a 3-dimensional tube, so only the very center, and then all the other velocities slow down as you get closer to the edge. Okay. Now, what the model is then, they've taken that backwards bullet that they have there, that has the arrows in it, and they're modeling it here, and I guess it makes more sense to talk about it this way, but I would turn it the other way. But anyway, in laminar flow, the fluid particles passing through a thin ring at a distance Ri from the center all travel at near the same velocity. So it's, again, just like we were doing before, you get a thin enough cross section. These out here are going very slowly. This one right in the middle is going in the fastest, and these would be decreasing velocity going from the center to the edge, or increasing going from the edge to the center. So in a given ring, as long as the ring was small enough, then they're going to be approximately the same speed. All you have to do to make them closer to the same speed is make the smaller ring smaller, okay? And then you get closer to the same speed. So then you talk about the ring just of this width. Its area is, okay, and then you have to do it a little bit more. Think of this as the width times the length. That's its area. Of course, this is a circle, so sort of act like you cut that circle right there, lay it out flat. Doesn't quite go flat, but make it as close as possible. Then the thickness of this is your delta R. Okay, ring of width delta R, and the length would be the circumference, which is 2 pi r sub I. That radius of this one right here, r sub I. And what we're going to do is integrate this from 0 to capital R. And that'll get all the rings in there. So that gives you your area. Your velocity as a function of r of I, how far you are from the center, that's fixed. So it's not constant going all the way out, but in that ring, it's about constant. So that's a function of R, function of Ri. So laminar flow, the fluid particles passing through a thin ring at a distance Ri from the center, all travel at nearly the same velocity, and that velocity would be, because velocity is a function of how far you are from the center, at that distance from the center, Ri, you're pretty close to the same velocity, will be Ri. Okay. So, if you're then looking at the total flow rate would be you're integrating from 0 to capital R. Capital R is the radius of that pipe to whatever it is, and you're integrating different delta R's. Okay, the 2 pi r dr would be the area of that. 2 pi r is the length of that ring, and the dr would be the thickness of the ring, so that would give you the area of the ring, and then your v of r, velocity, as a function of that r in that region would be your third dimension. So this would be a length for time, and a length. Well, that gives you cubic feet per, or cubic centimeters per minute, whatever your time is. So if this velocity is centimeters per minute, then you'll get a flow rate of cubic centimeters per minute. Okay, 2 pi is just a constant here on the outside. So there's your flow rate in volume per time. Whatever your volume is, whatever your time is. Okay. So there's your flow rate equation for laminar flow. Okay. So I think example 6 is going to deal with that, but there's no slide for it, so we'll write it here. Now, here's something on Poiseuille's law. So was Poiseuille a famous physicist or mathematician? No, he was a physician, okay, not a physicist, but a physician. And what is he doing messing with laminar flow?
What's the difference?
Huh?
What's the difference?
A physician is a medical doctor, and a physicist is a physicist, one who studies physics. But they do have the first several letters that are very similar. Okay. Well, why was he interested in laminar flow anyway? Why would physicians be interested? Blood flow. Your veins, your arteries and stuff act like little tubes, okay, carrying the flow at a pretty reasonable rate of speed. You don't want it turbulent in there. That's not good. So it is laminar flow. So he used this, he came up with this for blood flow in arteries, veins. I think it even works for capillaries. Okay? Sorry, I'm clogging up. I don't know why. According to Poiseuille's law, by the way, if you want to write on Poiseuille, you could. Probably Poiseuille's law would be a little more interesting to you, but he had to do math to get there. Those would be potential paper topics. Which my perfect class, how many have I gotten in so far? 9. And my earlier class today, 2 already at least. So, come on, perfect class. Okay. According to Poiseuille's law, the velocity of the blood flowing through a blood vessel of radius r centimeters is V of r. So here's Poiseuille's law. V of r, this gives you the velocity at any radius r in centimeters, is some letter k, that's a proportionality constant, r squared minus little r squared. R being the radius of that blood vessel, and little r being what portion of the radius you're at any time. That's your variable, little r. Where little r is the distance from the center of the vessel, again in centimeters, k is some constant. Okay? It says calculate that flow rate, q, as a function of capital R, your blood vessel radius, assuming that the k, and we're going to assume the k is 0.5 per centimeter second. 0.5 centimeter second to the minus 1. That's per centimeter per second. Okay. So that's your velocity as a function of radius. And it has a squared dependency there. Okay. So, using this formula here, your flow rate Q is 2 pi times your integral from 0 to capital R. We don't know what that is. We're just going to use that as a variable. Okay? R, that's your radius, 2 pi R, that's from your area. V of R, which we're given here, this K we can go on and pull on the outside, so it's out there. And then we'll have capital R squared minus little r squared. And then finally dr. Okay? Now, we even know the value for that K, 0.5. So multiply 0.5 times 2, and what do you get? 1. Okay? So this is just going to be pi. And let's go on and do the integral. Now, one thing to remember, even though that's a pure number pi, it has the units of k, which is per centimeter per second. So got to remember that as units with it. Okay? Can we do this integration? What would you probably want to do first? Actually, there's a couple ways you could proceed with this one. How would you like to proceed? I hope this isn't too suggestive. Let's go on and multiply that through. I mean, in reality, you could do a substitution because the derivative of this is partially that. But that's a lot of work. Whereas you just multiply through, you got a polynomial. And those are really easy, aren't they? So let's do that. So that would be, okay, little r, okay, yeah, you should have done the big R squared first, but that's fine. Minus r cubed, and that's dr. Now I think I'm ready to do the integration. And what would that be? The capital R is a constant. So that'd be r squared, that's just a constant. r squared over 2. Is that what you said? I thought so. Okay. Okay, I'm sorry. No, I'm sorry. You're right, but I wrote the wrong r. Well, don't have my hesitation there. That's r 4 over 4. Evaluated from 0 to r. Okay? That's going to be pi times r to the 4th over 2 minus r 4th over 4. And since r 4th over 2 is 2r multiplied by 2 over 2, that's 2r 4th over 2 minus r 4th over 2. Shouldn't have meant to just point at that, and I made a mark over it. That would be 2/4 r 4th minus 1/4 r 4th would be pi r 4th over 4. Right? You agree with that? Okay. And that gave that the flow rate is proportional to the radius of that blood vessel to the 4th power. Whoa! Okay? That means for a very small capillary, which is really, really tiny, that radius to the 4th power is a very small flow rate. Okay? So what that means is your blood vessels, as they go from big, like your big arteries that are carrying blood down to the muscles that you're using, okay, they have to split into an awful lot of little capillaries to keep that flow rate going, so you don't have backup or high blood pressure. Okay, so that's why it's pretty important to keep those radius. Because think of this: even a reasonable size artery, what if you get some plaque growing around it? Now effectively your radius is much smaller. So now the flow rate is much less, and that's exactly what leads to heart attacks. If you have blockage in the arteries that actually are feeding your heart, then suddenly they're not getting the blood you need, and yet you put more demand on it, and you can have a heart attack. Hopefully you can't. Y'all are both pretty healthy people. But I have a brother-in-law who I think it was just last week, he was a pharmacist for the VA, worked there for probably well more than 30 years, and does his yard work, does all the work, goes to the gym, all this kind of stuff. He had a heart attack last week. Wasn't a major one, but it was one. He's just getting out of the hospital today, so it can happen, but my guess is some of those blood vessels got smaller and smaller, so now with blood flow, the flow rate got less and less and less. Just a little bit of reduction can greatly reduce the flow rate. Most of the time you make up with that with a little more pressure, you still keep enough going. But when it gets too small, it can be a serious problem. Okay. And sure enough, and this is measured in centimeters cubed per second. Now, where do we get those units? Well, remember this pi had the K, which is the unit for that K was 1 over a centimeter and 1 over a second. So 1 over centimeter second here. What you have here is centimeter to the 4th, and what you had down here was centimeter second. So one of these centimeters, took one of those out, and sure enough, that gives you centimeters per second. cubic centimeters per second. So that's why that K, even though you lost the number because it multiplied by 2, you didn't lose the units. All right. Now the book didn't worry about that. They just said these are the units. But that's what I kept up with. All right. Any questions on flow rate? Next thing we're going to talk about is average values. Okay? Now, y'all are both students. You've been students for most of your lives, right? So you're used to figuring average values, right? Or at least averages on tests, or averages at the end of the term, and averages that you hope they're going to curve, right? No, you don't think about that. Okay. How do we do averages? Well, if they were unique points, like only this point, this point, this point, this point, that point, that point, those are your grades, okay? Came through at the end there, maybe pulled the average up. But that was finite things, okay? The average values of the f of x's at the points x of 0, 1, 2, 3, up to x of n would be r sub n. Now they haven't defined that. That's the total, the sum of those. Okay, sorry. They're not talking about finite points. What they mean there, this is the total we better read the problem because it's a slideshow that's leaving a lot out. We cannot define the average value of a function f on an interval a to b as a sum because there are infinitely many values to x to consider. But recall the formula for the right endpoint approximation. Is that what they're talking about? So if you did a right endpoint of that approximation, you did this little rectangle here with that right endpoint, this one with that right endpoint, this one with that right endpoint, this one with that right endpoint, and this one with that right endpoint. That's not too bad. These undershot by varying amounts, these overshot by varying amounts. That would give you a bad idea of what it is. Okay? And if these are equally spaced, then you just do b minus a, that's the total length, and the total right end, the summation of all these right endpoints. That would give you a pretty reasonable idea of what the average value of that function was. You just pretend that those are discrete values over, and those little rectangles represent the same area under the curve. They probably don't, but they can be a good approximation, especially if you have a function that's not monotonic. Monotonic up, the right-hand endpoint is always going to overestimate. Monotonic down, right-hand endpoint is always going to underestimate. One that goes up and down, you're a lot better chance of getting it well, okay? So that would be how you would estimate that for finite delta x's. What if you had infinitely small delta x's? Then your average value becomes this. You still do the 1 over b minus a. That's your basically the length of that x interval. But then you sum, basically this is the area under the curve, right? That's what that is. Area under the curve divided by the length of the curve, the length of that box, and that gives you your average value. Okay? The next slide will make this make a little more sense, but that's your how we go about getting the average value. This figure, I guess, shows it maybe a little bit better. Okay? All right. Here is the first lobe of the sine wave, from 0 to pi. That's how your sine wave looks, right? Okay? Goes up to 1 here, starts at 0, ends at 0. Okay? First lobe looks like that. What's the average value of that? Well, you have values anywhere from 0 to 1, but what's the average value? Well, if you take the same area here, which you can get by the integral of sine x dx, that gives you your area, okay? Divide it by the length here, and that gives you the average. So the gray part here and the tan part here supposedly have the same area. Yeah, that looks pretty reasonable. You take half of this and it covers that, the other half covers that. Yeah, that looks like the same area. And that's exactly what you get. The area under the graph is equal to the area of the rectangle whose height is that average value. By definition, it has to be. The area under the graph is the integral of sine x dx. And then that is the area of the rectangle, which is length times width. Width is this part, so the average value, that would be the height of it there. So that was actually the next problem. So let's do that. This is example 7. Find the average value of f of x is equal to sine x. So x, okay, from 0 to pi. And it really doesn't matter if you put brackets, parentheses, it doesn't matter. Okay, how would you do this? What was the formula we just had? B minus A times the integral from A to B of f of x dx. Okay, let's plug in what we got then. What's your b in this problem? Pi. And the a, 0. I can subtract 0. I've already done it. Okay. And this will be 0 to pi. Okay. Your f of x was sine x dx. Okay, so this will be 1 over pi. And what's the antiderivative of sine x? Oh, really? Negative cosine x. Okay, all but that little sign there. Okay, negative cosine x, and you evaluate that from 0 to pi. Okay. Be 1 over pi. And then what is negative of cosine of pi? What is cosine pi? Second? Negative 1. And negative of negative 1 is positive 1. Okay, minus a minus, which is plus cosine of 0. And what's cosine of 0? 1. So 1 plus 1. Didn't know you'd be doing such high-level math today, did you? This gives you 2 over pi. And that's what they show here. That's how you get it. Boy, when you have minus signs and you're subtracting and you're plugging in, those signs can get so wacko. So take it easy, take it slow. And 2 over pi, by the way, is pretty close to 2/3 because pi is close to 3. So that's something a little bit less than 0.667. It's 0.637 approximately. So, and that's about almost 2/3 of the way up here. Not quite 2/3 of the way up. The average value. All right. How about cute little pictures? Don't you like cute little pictures? This is something they call a bush baby. Cute little name too, isn't it? Okay. The bush baby.
Well, he's on a tree.
What's that?
He's on a tree,
Only what?
I said he's on the tree.
He's on the tree, yeah.
So it should be a tree
Okay, I didn't hear all that. I'm not sure. I'm not sure it was worth it either.
I said it should be a tree baby.
A tree baby, not a bush. I got it. All right. Okay. Shame on them. They named them wrong. Okay. They have very big bushes there. He's a very small animal. Okay. Okay. A tree baby can jump as high as 2 meters. Okay. A center of mass rising more than 5 body weights. Okay. By contrast, Michael Jordan rises at, y'all remember who he was? Okay. I remember Michael Jordan. Rises at most 6/10 of a body weight when executing a slam dunk. Okay. Now, what do you remember best about Michael Jordan? Huh? His jump. Okay, I thought he'd remember something even better. He's a baseball player. Yeah. He played for the Birmingham Barons. Yeah. For a short time. I think maybe 2 seasons. Record crowds everywhere they went to see Michael Jordan. He was in the White Sox organization. I think he couldn't hit a curveball. Is the only reason he didn't make it to the big leagues. Yeah, that's usually what gets people. Okay. You have a curveball? Good. All right. Now, that's what we've got. Why are we bringing him up? Okay. Well, find the average speed during a jump if the initial velocity, vertical velocity, is v sub 0 is 600 centimeters per second. And it says use Galileo's formula for the height. And here's Galileo's formula. H of t, okay, is equal to v0t minus 1/2 gt squared. Okay? Now, since they gave us v0 is equal to 600 centimeters per second, which is pretty quick if you think about it. 600 centimeters a second. That's 6 meters a second. I'm about 2 meters tall, so the ceiling's about 3 meters tall, and 2 floors, he can jump that in 1 second. Okay, or at least that's his initial velocity. That's pretty fast. Okay, has to be for him to jump that far. Okay, so that's his initial velocity. Okay, now if you're in centimeters, then your g, does anyone know what g is?
Gravity.
Acceleration due to gravity. And what that value is? Okay, he said 9.8. What units? Meters per second squared. Acceleration has to be length per time per time. So that'd be meters per second squared. But what's wrong with this problem right now? Yeah, you got different units, centimeters and meters. Seconds are fine. Now, if one of those were in minutes, you got more problems. But your seconds are fine, but so you have to convert the meters to centimeters. And how many centimeters in a meter? 100. Okay, so that would be 980. Say again? What's that? You could do that too if you wanted to go that route. Let's see what the rest of the problem is. It says use Galileo's formula for the height in centimeters. That's how the problem called for, so that's why we went the other way. You could have done it the other way and then come out with how many meters. They said in centimeters. Okay. Now, that gives us height. Okay? And what's the question for? Find the average speed of a jump if the initial vertical velocity is that. Now, they're not physicists, okay? And so how they set up this problem, I find a little bit lacking, okay? It seems like to me the best way to do the problem, and I may be wrong on this, but if you're looking for average speed, why don't you do in terms of speed or velocity, actually speed, from the very beginning. Their graph, they do it, okay? But they don't do anything else that way. So it seems like to me if you want the average speed, you do what is velocity as a function of time? Derivative of your height as a function of time. We're only talking about vertical. We're not talking about any other dimension. So that's that. That is your dy dt. That is your speed. So this would be v0 minus taking a derivative. I shouldn't have done that for you. I should have made you do it, okay? Take a derivative with respect to time. Not that bad, is it? Okay. Sorry. All right. Take a derivative with respect to time of that function. Huh? Yeah, of h of t. V0, yeah, but you're taking a derivative. To the first power, 1 times v0 times t to the 0, which is 1. That's just v0, right? Okay? I know this is Cal 1, but you didn't have to forget all that. What would this part be then? G, T. I like these GTs. I went to Georgia Tech. Never mind. Okay. All right. That is your velocity. Now, is that the same as speed? Not quite. And that's what the graph is showing here. And what they're showing here is the graph of your velocity function. The dotted line when it goes down here, because guess what? When that tree baby jumps, okay, it says the average, find the average speed during a jump if the initial vertical velocity is that. Well, the jump is counting from when he went up until he lands, okay? And if you plotted that, you're going to get a parabola, all right? Because the height is a function, that's going to be a parabola. His velocity up here is 0. It's positive going up, negative coming down. So that's why the velocity goes down like this. But speed is the absolute value of the velocity. So this part, you plot back up there. So basically, you're doing the derivative from t equals 0 when he's on the ground until he comes back to the ground. Okay. Now, that then says, where is that velocity equal to 0? Okay? In other words, what is the time at which the velocity equals 0? Okay, when is that equal to 0? And that's what they do for their units there. They set this equal to 0, and this will be 600 centimeters per second minus 980 centimeters per second times t is equal to 0. Well, that says 980 t is equal to 600, right? This is per second squared, sorry. Equals 600. I'm leaving out the units for now because they just get so messy. So this will be at t is equal to 60 over 980, which would be, and they like to say, 6 over 9.8. Fine, if that's what you want to call it. That's the place where that goes to 0. And then after that, the speed's the same coming down as it was going up, but just in the reverse order. So basically, this is what you're finding the average value of. Okay? And because these are exactly the same, we're assuming no air resistance. Okay? So you don't have any change. This area is the same as that area. Right? So the average value of this whole thing would be the same as the average value of power, wouldn't it? So why don't we just do our average speed again? Let's see if it gives us the same answer. Okay? So rather than have to worry with absolute value functions and all that kind of stuff, let's just do it. Okay? So what we'll be doing here is the average value of what? Velocity. So V, I'm going to put V bar, average velocity, okay, is equal to, and it's just going to be the first half of that. So 1 over 6 over 9.8 minus 0 times the integral from 0 to 6 over 9.8. Why don't they just go on and give us a number there? But they're stringing it out here. Times this velocity vector, and that would be this right here. Here is your velocity, which is 600 minus 980 t dt. Okay? Let's see what we get. 1 over 6 over 9.8. Okay. You know what? I know what that is. Okay. Not exactly, but 1 over a fraction, that would be the same as 9.8 over 6. Isn't it? 1 divided by this would be 1 times the reciprocal, so that would just be that. A lot less writing. Okay. So there's the constant in front. Now do the integration. Say again? 600t minus 490 t squared, evaluated from 0 to 6 over 9.8. You just drive me crazy with those fractions. Okay? So, I'll let you plug that in your calculator. And then, no, I won't. I'm going back to what I had before. 1 over 6 over 9.8 times 600 times 6 over 9.8 minus 490 times 6 over 9.8 squared. I'm going to do it that way. Okay? And here's why. This will cancel that out, and we'll cancel one of those out. Right? Okay. Makes life a little easier. Okay? So this will be 600 minus, and then 490 I want to do it another way, but I won't. I'll keep doing this way. 6 over 9.8. Okay. Well, I know that 490 is 2 times 980, right? So 9.8 would go into 980 100 times, right? So it would go into 490 50 times. You can do it on your calculator, but check that. 490 divided by 9.8, I almost guarantee you'll be 50. Want it? No? Huh? Is it? Okay. Multiply 50 times 6 and you get 300. So it's 600 minus 300, right? Which is 300 centimeters per second. So his average speed is that. Well, guess what, team? Okay? If the speed is constant coming down and constant going up, the rate of change, then basically there's his average speed right there. This would be what they call uniform motion, right? Constant velocity, constant acceleration, not constant velocity, constant acceleration. So the average speed is exactly half the maximum. If it's going from there to there. So you could have saved yourself a lot of work. But our whole idea was to do integration. So we did it with those weird numbers, but still, in retrospect, it's exactly half of this speed. Okay. So yes, that makes sense. What doesn't make sense is doing it that way. But we did. All right. And the book is happy now. All right. Now this leads to one of the most significant, okay. No. No. Okay. Hit the wrong button. Now, this looks like that figure we had before. In fact, I first thought they were just repeating it. It's not quite. It's just some curve. It looks a lot like a sine curve going from 0 to 5, but not necessarily. It's just some curve there. Okay? The function f of x takes on the average value m at the points where the upper part of the rectangle intersects the graph. Okay? Sure, that makes sense, right? This is the average value m, and that isn't halfway up, whatever it is. So the curve has that value here and here. Okay? All right. So, big deal. That's leading to something. And here's what it's leading to. It's called the mean value theorem. That doesn't mean it's a really ugly value. It doesn't treat its neighbors well. That means the average. Mean value theorem for integrals. If f of x is continuous, some continuous function on the interval a to b, then there exists a value c somewhere in the interval a to b, such that the f of c is exactly its average value. This is the average value of the function on there. And this says there is some value in c in which that function is that. So in other words, the function has to have at least one point in that interval where it's at its mean value. If f is a continuous function, yeah, it's got to have its mean value somewhere in there, and that's the mean value theorem. Okay? Doesn't seem like anything earth-shattering, but it's a very, very useful theorem. That's that. C is that point where f takes on exactly its average value. And that's all they do with it, okay? They do a little proof here, and you certainly can look at that. And that finishes 6.2. Now, do y'all want to do preliminary questions? 6.2. You tell me. Yay or nay? Second? Yeah, let's do it. Okay? And this had better be the last slide. It is. Okay. What is the average value of f on 0 to 4? We're looking for average value of f on 0 to 4. If the area between the graph of f and the x-axis is equal to 12. If the area between f and the x-axis is 12. So what would be the average value?
Is that if area is 12?
Area is 12, right. Making fun of my writing, I can tell. Okay. I'll remember that. Okay. Guess what, team? This is the average value of the function, isn't it? Okay. This is the area of the function, right? So, this, they told us here, is 12. And they're looking for the average value, which is all that. And so it says average value is equal to 1 over b minus a times the area. Okay, they told you the area, 12, and they told you b and a. What is that? That would be 4. So what is the average value? 3. Okay, that's all you really had to do with that. They masked it well, making it seem like it was going to be something difficult. It wasn't. You know, it was pretty straightforward. Now, why is my paper not in the right place back here? I do not know. So 6.2. Whoa, not that. This one is indeed 1. I know why it isn't, because we didn't do it last time. Okay, let's do, you got that? Okay, let's go to 2. Yeah. All right. All right. Find the volume of a solid extending from y equal 2 to y equal 5 if every cross-section has an area of 5. So we want the volume of a solid extending from y equal 2 to y equal 5. Okay? If every cross-section area as a function of y is equal to 5. So let's kind of draw this. Okay? Here's 1, 2, 3, 4, 5. Okay? And here's some cross-sectional area here, but that's the same cross-sectional area for every piece here. Every piece has the same cross-sectional area. And those are 5, isn't it? Yeah, the cross-sectional area. If A of y is a constant 5. Okay? So what would be the volume of that? Okay. Turn back one page, you'll see the formula. V is equal to the integral from A to B of A of y dy. Right? Where A is the cross-sectional area. Right? But that's a constant. It's not, it is a function of y, but it's a constant. So this would be the integral from 2 to 5 of 5 dy. Can you integrate that for me? Might be a little easier, but not much. But take the 5 on the outside, the integral from 2 to 5 of dy. Can you integrate that for me? Y evaluated from 2 to 5, and that would be what? 5 times. Say again? 5 minus 2, which is 3. Didn't need a calculator, okay. That would be 15. That's it. Well, that's what I was trying to show you here. If every area here is 5, every one is 5, whatever its shape, it doesn't have to be a cylinder, but if every area is 5 from 2 to 5, they're all 5, then it's just 5 times 3. Because that's the height of 3. So I do this. Oops, I didn't get it right. I should have gone from there. Sorry. But from here to there, that would be 3 times 5 would be 15. Without doing the integral. But y'all like integrals, so you want to do those. Good for you. Getting your money's worth. Okay. So, let's go to, is that okay? Okay. Let's go to number 3. What is the definition of a flow rate? Yeah, you can go back and read that if you want to. I'll read you what they say in the back. Flow rate is the volume of fluid passing through a cross-sectional area at a given point at a given time, per unit time. Flow rate. How much volume goes through a given area at a given time. Okay. Number 4. Which assumption about fluid velocity did we use to compute the flow rate as an integral? There was an assumption involved. And it has to do with what kind of flow we were dealing with. Okay, the not too fast flow, that's it. Often called laminar. Because if it's too fast, it goes turbulent. Those are, miserable to try to calculate. Laminar flow. I think that's what they mean. Let's see what they say. The fluid velocity depends only on the radial distance from the center of the tube. Yeah, which is another way of saying it's laminar flow. Okay. Number 5. The average value F on 1 to 4, this is almost what we had before, is 5. Find the integral from 1 to 4 of f of x dx. So, average value of f on the interval 1 to 4 is 5. Find the integral from 1 to 4 of f of x dx. How did you get that? Okay. Yeah. This, the whole thing is the average value of the function, right? And that's 5. They told us that. Okay. So to find what that was, that would be, just this part would be 1 over 3 times this function here. And sure enough, that would have to be 15 to have that equal 5. So you're right, it would be 15. Let's see if they got it. Oh, they did. They got it right in the back. Good for them. All right. Homework exercises, then do any of the odds 1 through 7, any of the odds 9 through 13, any of the odds 15 through, 37. There's quite a few there. I wouldn't just do 1 or 2, do a few of each. Okay? Then do any of the odds 39 to 47. And then do any of the odds 49 through 61. Then try 63. 65 basically is just a writing exercise, it says. But you could think through that to see if you can do 63. And then they have some further insights and challenges. If you want to attack those, you certainly may. Any questions on 6.2? Okay, if not, then let's move on to 6.3. See how long it takes this to open this time. Boy, this morning, very, very slow. It's going a little faster here. Good. All right. Okay. 6.3 is dealing with things we call volumes of revolution. Okay? Here is a triangle. Okay, in the xy plane. What if you were to revolve that around the y-axis? What do you form? A cone. And that cone is in 3 space. It's not just in the xy plane. So that would be a cone. What if you revolved it around the x-axis? The cone sitting this way, it would be a much bigger this way, but it's still going to a point there. That would be a cone. What if we had a semicircle and you revolve that around the x-axis? Say again? A sphere, exactly. What if you revolve that around the y-axis? Hemisphere. No. If you go this way, you still don't get anything down here. It's just that you get half of this here, half a watermelon. So, I don't think I can get them all on at once. Let's get these 2 at once. Okay. So what it says here, the right circular cone and the sphere are solids of revolution. Okay. Just depends on what you're revolving. Okay, that's all they're saying there. Now, so let's say now we just have some function. That line that went down there, that was a function of x, okay? That hemisphere is a function of x, okay? So let's say we have any old function. Doesn't have to be a nice regular thing. Any old function, as long as it's always non-negative. In other words, it stays above the, let me go on and get this, above the x-axis, okay? And you revolve it around that. You can revolve it this way or this way. This one basically just revolves that way. But if you do that, you get, and these are just aligned in a semicircle, but you can have any old shape there. You revolve it around some axis. Doesn't have to be the x-axis, but then you're going to get a volume of revolution. Okay? They won't be as regular as this, and there'll be a little more work to determine. But, for instance, what if this is what you had? Now again, the requirement is f of x has to be never negative, and that one isn't. Okay? The other two actually became 0, but they never went negative. This one stays strictly positive. Let's revolve that around the x-axis. Well, we get what looks to me like a Christmas tree base. Okay? Something like that. Okay? I would have shown that first and then this. Now, any cross-section you have here of this thing, you revolve it around because you're revolving this thing all the way around. That's going to form a circle. Okay? So every incremental base, I like to call that a dx there, is going to be, but x is just a single value between a and b. That's going to be a circle. Okay? And we know what the area of the circle is, right? Pi r squared. I always thought pi were round, but pi r squared. Okay, so if that's your circular area, and you integrate that area from A to B, that should give you the volume. Should. Okay? That's how we get the volume of revolution. We call this method, I haven't called it this yet, the disk method. We take a disk and we extend that from A to B. Okay? We'll get there in a minute. I jumped ahead. Okay? Well, no, it's right here. I thought they were going to take more time with it, but here it is. The volume of revolution using what they call a disk method. If f of x is continuous, f of x is a continuous, boy, it becomes a pain in the neck doing a volume with it. Okay? So if f of x is continuous and always greater than or equal to 0 on the interval a to b, then the solid obtained by rotating the region under the graph about the x-axis has a volume. Now, the capital R here stands for f of x. Okay? I almost wonder, why not call it y? That's what we usually call it. We call it capital R. That would be fine. Well, why? Because that's the radius of that disk that you're talking about. So the volume is the area, pi r squared, so that r is your f of x. So why even introduce, well, I guess so, times your increment dx, summing over that, integrating over that, from a to b, that gives you the total volume. So it's pi times f. I don't like this notation. I like to say f squared of x, because you could look at that in a weird way and think that's f of x squared rather than f of x squared. Okay, so I like to put the square here so you know it's the function being squared. F of x squared. Yes. That's your volume of revolution. Using the disk method. There you have a function of x, revolving that around the x-axis. Everything works out pretty neatly. So let's do example 1. Any questions? Okay. Here's example 1. Calculate the volume V of a solid obtained by rotating the region under y is equal to x squared. There it is right there. Let me blow this up maybe a little bit. Okay. This is the region we're talking about here. Y is equal to x squared. Now, they have really extended the x-axis and compressed the y-axis here. Because this would be 0, 0. If this was 1, it should be 1. So they've really squished it down the y-axis here, and 2, 4. So we know it's going to there. But it really doesn't matter. Y is equal to x squared, that's the curve. Okay? Calculate the volume V of the solid obtained by rotating the region y equal x squared. See, it's equal to 0 at 0, never goes negative. Okay? About the x-axis for 0 less than or equal to x less than or equal to 2. Okay? From 0 to 2. Revolve that around the x-axis, and you get a maximum. Okay, or something like that. Okay. So, let's do it. What is the volume? Oh, goodness gracious. Okay. V is equal to, how does that go? Pi, integral of, second? Okay, from 0 to 2. That means you're doing a dx, because that's what x going from 0 to 2. X squared, that's your f, or your y, squared. And that's all there is to it, isn't it? Okay? Can we do that? This is equal to pi times the integral from 0 to 2 of what? Say again? Okay. Let's take it a step at a time. That would be x to the 4th dx, right? Is that what you were doing? That would be pi times, and then what would that be? Fifth over 5. Is that what you said? Okay, I thought you said x to the 4th over 5. I thought, how did he get that? Okay. Okay, I'm sorry, I can't hear well. And you're doing from 0 to 2. And does anyone know what that happens to be? 2 to the 5th, 32, isn't it? Okay, that'd be 32 fifths. I can do the 0 part. Okay, done. So that'd be 32 pi fifths. Okay, let's see what they did. 32 pi fifths pi. Okay, doesn't matter how you phrase that. Okay. Now, that's the disk method. Anytime you have a function, say of the x, function of x, and revolving around the x-axis, you can do it by doing those little disks. I like to say those are dx's, and the area of that is a of x, which is your circle, which is pi x squared dx. Makes sense, okay? Now, you could have also been going, if you had revolving around the y-axis of this same thing, then you would need to probably change that to x equal y to the 1/2, and then do that, okay? And that's doable too. If you have x as a function of y, and then do dy's, then that can work too. Other times, they're not very easy to do that way, but we won't get there yet. Before we go there, we want to do something else. We don't want just a function of x. We want to have not just a disk, we want a washer, okay? Because our clothes are dirty, okay? So we will do the washer method. So if you're trying to do the area between two curves, this will give you a washer rather than a disk. The region between two concentric circles is called an annulus, or more informally, a washer. Okay? So to get the area, now we don't do it the way we did before, which is doing a dx here and then stretching that out. Nah, we're doing it a little more precisely now. We do the area of the outer disk, which is the whole area, and then subtract the area of the inner disk, and that leaves the area of the washer. So that's what we do. And since the areas are pi r outer squared minus pi r inner squared, pi's are the same, pull those out, it's just the difference between those radii squared. Okay? And the radii are usually functions of x, f of x, g of x, something like that. Okay? So what does that lead to? It leads to the volume between area between two curves being revolved around an axis would then be pi from A to B, whatever the limits on your x's are, of your outer radius squared minus the inner radius squared, which would be pi times integral from A to B of, I like to call that f squared of x minus g squared of x dx. Okay? In other words, the volume of the outer one minus the volume of the inner one. Just do it on one. Okay? That's the washer method. Okay. So here we have the two functions. Let me blow this up. I think I can get it all on here. Oh, I can't. Okay. So let's start with this part. All right. So you have two functions, f of x and g of x. And right now we're keeping them greater than x, greater than or equal to x, both of them are. So we're going to revolve that around the x-axis, and that's going to make an angular ring around the x-axis. Okay? And for any point in between the x, between A and B, this A and that B have nothing to do with this A and that B. They're just values, okay? So this is your g of x, this is your f of x at that value of x. So what you've got is the area of this washer in between those, okay? And what is that area? But the area of the outer one, pi b squared minus pi a squared. Well, yeah, those values are b and a that way. Then that's what you got. The f of x squared minus g of x squared times pi. And that would give you the volume. Whoops, I hit the wrong thing. Backward key. Okay. So it generates the washer when rotated around the x-axis, and now you would have, that looks a little bit more like a Christmas tree stand. No reason to have a bulge in here, but it's got one. That would be fine. You have a place to put the trunk of the tree. But that would be the volume of that thing. Minus the inner part, just the outer ring. Okay. So, let's do example 2. I believe this is the thing. Let's see if it is. Can we get it all on here? I think so. Okay. Find the volume V obtained by revolving the region between y is equal to x squared plus 4 and y is equal to 2 about the x-axis, okay, for between x equal 1 and x equal 3, between 1 and 3. Okay, I think our pictures are pretty good, so let's do it. What would be the volume of that? That's a Christmas tree stand for a very thin stem tree. What would be the volume of that? Pi. integral from 1 to 3. That means this is going to be a dx. And x squared plus 4, is that what you said? Really? Squared minus 2 squared. Okay, I'll buy that one. Okay, so let's figure out what that is. Pi times the integral from 1 to 3. You know, you're going to need to square x squared plus 4 for me. What would that be? Okay, a little louder, I can't hear.
Would be x squared plus 4, and then you put that in parentheses.
Okay, you faded out at the end, I couldn't hear. X to the 4th. That may be what you're saying, I couldn't hear. More? Huh? Plus what? 8x squared. I'll buy that one. Okay. Yes. Plus 16 minus 4, which would be plus 12. Okay. I think I'll agree with that one then. Okay. Can we do that integral? Pi times x to the what? I thought that's what we said, okay? Over 5 plus, second, with the 8 in front, right? You said that, okay, good. I love these numbers, okay. That would be pi times, okay, 3 to the 5th. 3 to the 4th is 81, right? Because it's 3 squared is 9, and 9 squared is 81, so that'd be 81 times 3, which is 243. 243 fifths plus 8 times 27. Oh my goodness. 56. 216? Yeah. 216 over 3. Whoa, that's not right, is it? Yes, that's right. Let's back off and make that easier. Do you mind? Okay, why didn't I see this before? 3 cubed over 3 would be 3 squared, wouldn't it? If you did 3 cubed divided by 3. Forget about the 8 for now. 3 cubed divided by 3 would be 9, right? 27 divided by 3 is 9. 9 times 8 is 72. Isn't that a little easier? I know you love your fractions, but give them up if you need to, okay? And then plus 36 minus 1/5 minus 8/3 minus 12. Okay. Still a pain in the neck, isn't it? Okay, pi times, and that will be 242 fifths, right? Minus 8/3. Get the fractions out of there, okay? Now, 36 minus 12 is 24. 24 and 72 is 96, isn't it? Okay. Now, the bad news here is you got to get everything into 15ths. Right? All right, pull out the calculator. We'll get it done that way. Multiply the first one by. Okay, say that again. 2126. That's your final answer? Did you do it all? Okay. All right, so this is 2126 15ths pi. Okay, let me just take a look at that. Yeah, that looks reasonable. Oh, look at that. Nice round number. 2126 15ths pi. Okay. Why they do that, I'm not sure. But yeah. Not quick enough. Okay, go ahead.
X to the fourth.
Right.
How did that happen?
How did this happen? Oh, okay. Sorry. I should have backed up and done it because I knew you were starting to do it. Okay, you can do it one of two ways. One way is x squared plus 4 squared means x squared plus 4 times x squared plus 4. Right? Isn't that what it means to square something? Multiply it by itself. And then you can FOIL this, and that gives you x to the fourth plus 4x plus 4x squared would be 8x squared plus 16. You see that? Now the other way, if you don't want to write it out as FOILing it, square the first, x to the fourth, twice the product of the two, that's what you just did, double that. That would be plus 8x squared, and then plus 16 minus 4 plus 5. I skipped that stuff. Does that answer? What?
The 12.
Okay. How did we get it? Okay. This gave us a plus 16, and this gave us a minus 4. Right? I skipped that stuff. I shouldn't have, probably. I knew I was taking up too much. Okay? That answer it all? Yeah. Okay. Good deal. Glad you had the calculator. Okay. And the sad news is we're out of time. Okay. So we'll begin next time with example 3. Goodness gracious, why is that so long? Okay. Begin next time with example 3. Okay. Homework exercises in this group. We made decent progress there. Do 1 or 3 or both. Do any of the odds 5 through 11. Okay. Do number 13. Okay. No, leave off 13 for now. Just do 5 through 11. We'll pick up the rest of those next time. Okay? Good deal. Any questions? Okay, have a great weekend. Working math problems will make it great, won't it? Yeah. How have workouts been?
Pretty good.
Okay. Fitting right in?
Yeah.
Good. Did you know some of the guys before?
I kind of know of them.
Yeah.
Just because they played at high schools around.
That's I figured. Where did you go to high school?
I went to Springville.
Oh, okay. A little northeast of here, right? Yeah. There's a conference center or something up there we've been to a retreat at our church. I don't know. Was it 4-H or?
I think so.
4? Okay, yeah.
I actually met a guy one of my best friends from Huntsville. He's from Springville.
Oh, are you from Huntsville?
No.
Oh.
I went to UAH.
Oh, I see. Okay. Yeah.
He graduated, I think, 2015. Took a year off. Time short.
That's when I graduated.
I think 2015, 2016. So I know that he's a little bit older than me, but he started school at the same time.
Where'd you go to high school?
I went to Mexico.
Huh? McAdory. Oh, okay. You're closer. You still live out that way?
Yes, sir.
Okay.
10-minute drive.
Good deal. All right. Well, have a good weekend, and we'll see you. Where is UAB playing this weekend? I know it's out of town, but
I'm not sure.
Yeah.
I'm not sure.
not a football fan. Huh?
I am, but I'm not crazy.
Huh?
Not crazy about it.
Right. All right. Well, take care. We'll see you
See you Monday.
Monday. That's right. All right. If anyone wants to come to the math team, you can. All right. Yeah. All right.